Thank you, everybody. So before we get started, I just want to first of all thank Maggie. Where's Maggie? Wherever she is, she's probably very busy. But I wanted to especially just thank Maggie for making this all happen, as well as her team here, Brett et al. Making a conference like this happen and doing it on so successfully is, I know, it was not easy. It's been a lot of work for her, and Chattanooga is a beautiful place, and getting everybody here all at the same time on the same day is a nearly impossible task. So let's give a round of applause to Maggie and team, please. All right, so the title of this talk is Why Your Next or First Hardware Project Should Be Built with Nerves. Just maybe a raise of hands here. Anybody built any, like, more than 2 or 3 embedded devices before? Okay, we've got the Nerves core team. Okay, perfect. So, so yeah, the title is Why You Should Build Your Next or First Hardware Project, but I was really hoping to have this kind of audience where we could talk about your first embedded hardware project. So, as Brett said, I'm Todd Resudek. I'm a lead engineer at Weedmaps. It's not what you think. It's software that helps you find weed. So, yeah, I know a lot of people get that mixed up. So, on Twitter and GitHub, you can find me at Super Simple. On Twitter without the vowels. I've met a lot of new friends here, so follow me so we can keep in touch. So yeah, you might remember me from such embedded hardware projects as the Drizzle 2000. So the Drizzle 2000 is a smart sprinkler controller that I created with Nerves, and I presented on it at Lone Star Elixir this year. And the inspiration for this was I have a lawn, and I needed a sprinkler controller that could handle 8 zones. And so I was looking at these really expensive smart sprinkler controllers because I'm a technologist and I want to overdo everything and have technologies. And so I thought, these are the present day. I want to think about the future. I want to think about 2000. And so I built this. So it's a smart sprinkler controller. It does everything that the Ratio Series 3 does, which costs, I don't know, $200 or $300. And this cost me about $75 to make. And like I said, it's just as good as theirs, but even better. And it's also extensible, so you can do more with it. So that was last year's project. And I'm going to channel my Tim Apple here. Today, I'm introducing Breathe. All right. So some of you may have seen Breathe. I set it up on a table in the corner over there. You can check it out afterwards if you haven't. So this is a small desktop air quality monitor. This is what in the photography world we call an in situ photo. So this is actually on my desk, and yeah, you can see it's got lights, which is great. Lights are good. And I'll talk a little bit more about what's inside, but first of all, what inspired it? So I was looking at air quality monitors. I saw this device, which is beautiful, made by a company called Aware, and I was thinking, man, I could get one of these things. This thing looks great, and it will do what I need it to do. But it's $200, and I have 4 kids at home, small kids at home, so $200 is, that's like one new controller for the Nintendo Switch that they broke. That could be other things. And also, just being an engineering type, like I thought, well, that can't be that hard to build, right? What could possibly be in that? And so I set out on this project to see if I could build something like this. Here's another photo of the Breathe. So this is the inlet port that's on the back. And the front display, so it's mostly white. You can kind of make out where the LEDs are behind the white plastic panel. And so, yeah, so I guess the goal here, I hope for you, is if you're like most engineers I know, you have a Raspberry Pi in your desk drawer right now that you bought and you still haven't used. And so it would be great if at least one of you followed me on Twitter and said, hey, I grabbed that Raspberry Pi out and I finally got around to making my first embedded hardware project. Hopefully more than one, but at least one, and I'll be totally thrilled. So what's inside this bad boy? So this is the main component, the BME 680. So this is a Bosch sensor, very readily available. There's a few companies that make them. Technically, the Bosch sensor is this thing. It's about a 2 millimeter square silver box. The rest of this is the circuitry for power and comms. So this particular one is from Adafruit. Still, like the whole footprint of this thing is about the size of a nickel. But yeah, this is the BME 680. It measures temperature, humidity, barometric pressure in VOCs. So VOCs are volatile organic compounds, and I guess there's a few ways that you can measure air quality. VOCs are one. The easiest way to think of VOC is it's something that would make the air smell bad. And that could be like paint fumes, that could be lead, solder fumes, whatever. But there's other ways. There's sensors similar to this that instead of VOCs, they measure CO2. So if you're worried about CO2 content, you can swap it out with that, as well as particulate matter. So if you're worried about dust in the air, there's a sensor for that as well. But this one measures VOCs. It communicates via I2C, via I2C and SPI. I'll talk a little bit more about COM protocols, but I think you'll want to know if you get into a project like this, what communication protocols you're going to have to know to use a sensor. And this one costs $23, which is actually quite expensive for most of the components you buy for NERVS projects. Most of these things, so the first thing you do is you go on eBay and you spend about $9 and get about 40,000 little things that you're not exactly sure what they do, but you saw them, or Frank had them, or something. So you spend about $9, you wait 3 or 4 weeks for it to get shipped from China in a box, and you're gonna have 40,000 doodads, so that when you need them, you have them. And then every once in a while, you need to splurge on something like this that costs about 20 bucks. Let's try. All right, so the heart of the system is this Pi 0W. So as Justin talked about yesterday, NERV supports every Pi that was ever built. So this one is a 0W. It's got a 1 gigahertz ARM processor and 21 GPIO pins. So there's 40 pins there. Some of those are dedicated to ground. And costs about 10 bucks. So this Pi 0W it's a really small in size. The form factor was one reason why I chose it for this project. Plus it also has Wi-Fi built into it as well as Bluetooth. So, as you can see, it's pretty inexpensive to get started on NERV stuff. And then this is for the display. This is a Neopixel 8x8 matrix. This was like way overdoing it. So if you saw the Aware, it had single color LEDs for the display, which are like, you probably get 20 of those for around a penny. And this is a little bit more expensive, but this has 64 addressable RGB LEDs, so you can create 24-bit color on this, 64 different lights. So when I bought the display or started the project out, I wasn't exactly sure what the display output I wanted it to look like, whether it was going to be graphs or whether it was going to be letters and numbers. So I decided to go with this. This one costs 35 bucks. And like I said, you can, if you want to use single color LEDs, they're, inconsequentially inexpensive. And last but not least is this thing. This is a 5-volt fan. So measuring air quality is not good if you're measuring the same air over and over and over again. So this is connected to the inlet port, and normally you'd see these on computers as an exhaust fan drawing heat out, but in this case it's flipped around, so it's drawing air in. I've got a bullet point for that. Fan forces air. Okay. Did anybody not know that? Oh my gosh, for those of you that are watching this on video, like almost the whole room raised their hand. This is like, and there's, what is the count here, Brett? It's like 230,000 people here. This is like the Trump inauguration. So yeah, this costs $3.50. So yeah, once you get to tinkering, you're gonna have boxes and boxes of weird stuff like this, and people are gonna be like, "Dude, what are you building in here? You building bombs?" And like, you know, it's your house is gonna look like Radio Shack in the '80s. You know, you're gonna have everything. But yeah, so this is important. So the total cost on this project was about $70. And like I said, the most expensive part was that LED display, which you could easily forego that for some single color displays. So Justin talked a lot about what Nerves does or what it can do, but I want to talk about some specifics of why I chose it for this project or why you might want to choose it for your first project. So everything that all the components that I showed, everything that I've done on this could have easily been done, you know, written in C, been done on a platform like Arduino's, for instance. It certainly wouldn't have been impossible, but I think it would have been different and probably harder. So first, let's talk about C. So typically, embedded systems have always been built in C, and you know, for those of us who have never been a professional C programmer, or if it's been a while since you've been a C programmer, let me just first of all say C is really great, but let me show you like an example. This is a very trivial, contrived program. Honestly, I didn't even run it, so I don't even know if it works, but this is just to give you some examples of like what C looks like in case you haven't seen it before or in a while. So first thing with C, include basic stuff like standard I/O. Like you're going to need to add that. And then up at the top here of their main function, you've got to declare all the variables that you're going to use in the program and allocate, so in this case, allocate memory for this array. So now you're setting aside some memory on your system and saying, you know, I don't need it right now, but I'm going to be putting stuff in there later. And then down here at the end of the program, you got to make sure you free that memory up. Otherwise, you have what's called a memory leak. So does anybody recognize this guy, gal? Any My Little Pony fans? No? Okay, all right. I have 4 kids. So this is what a C program reminds me of. So this is Derpy Hooves, otherwise known as Muffins. And don't ask me why I know this stuff, man. So I consider like writing a C program a bit like Derpy Hooves. So she's a Pegasus pony, okay? She can fly, just like all the others. But she's not like the smartest, and like she could do anything, but you have to explain every single step along the way. And that's the way I kind of think about C programs. So let me show a little bit of the application code. So like I said, this could be written in C, but it would be a lot harder, and I'm definitely not smart enough to do it. So the first module is this measurement module. So this starts up a gen server, so it's running in its own process. It starts a connection, so in this case, it's an I2C connection on address 0x77 to the BME 680 sensor. So it says, okay, first thing, let's connect to the sensor, and then let's start a timer. Every 10 seconds, let's run this collect data function. And so the collect data function looks like this. It takes a snapshot. So a snapshot would be like, tell me what the measurements look like right now on the 680. Let's update our local state. So that's this next line here. So update my local state so I have a copy of it. And then let's spin up a task and shoot this up to the cloud. So in this case, I'm using a Google Cloud data store to store my data. So what's great about this is when using Elixir is you can start this in a task. So this task is running in a separate linked process, and it's non-blocking. So the idea here is that let's go about our business. Like I'm going to shoot this out and kind of forget about it. I'm running, every 10 seconds, so I'm grabbing, roughly 8,600 data points every day. If Google Cloud is down for a minute, I'm going to miss 6 of those data points, but I mean, that's trivial. I really don't need to follow the process and retry it if it didn't work out. So yeah, this is, an example that's great in Elixir that writing this in C would be more challenging and for me impossible. So here's the local data store. So we are using an agent. An agent is an abstraction of a gen server, which is just basically holding an Erlang term in local storage, in local memory. So like I said, every 10 seconds when we grab the data, we update our local agent. And this is where the display gets its data from. So when you see the display, it's pulling the data it needs to show lights from this local data store. And so this is the output module. The output module is in charge of making those lights show up. The first step of this was to get a baseline measurement. So these look like really weird measurements, but these numbers didn't just come out of thin air. So I started by hooking up the sensor in the environment that it's going to live in and running it for a few days to get an idea of where everything kind of averages out, so I know what normal looks like. And so this is what normal looks like in my home office. So pressure is, so gas resistance is how the VOCs are measured. So those are measured in ohms. And the pressure is barometric pressure. So normally in the US we use inches of mercury, which is kind of crazy. So normally, you're sitting between 20 and 30 inches of mercury. In this case, it comes out in hectopascals, which is a new one for me, but apparently 801 is a livable condition for humans. But that's normal in my house. So, and then the output module basically converts its current reading or compares it to the baseline readings and figures out how far away from normal we are. So you see these 8 function heads. They each relate to one light on the y-axis of the matrix display. So the bigger the difference, the farther away from the baseline, the kind of the center of the display you get. And this is what qualifies as AI in today's age. So I could advertise this as an AI, artificial intelligence air quality monitor. And then finally is the last part of the breathe module or output module is to grab that data every 10 seconds and then write it out to the graph. Another great thing about using Elixir and using a Raspberry Pi is that you can make a Poncho project out of this. So not only is this the embedded hardware that's gathering the data, sending it up to the cloud, et cetera, lighting LEDs, working with I2C sensors, but you can also host a web project on the same device. And so this is a Phoenix live view graph that I'm making. So I'm using live view to generate these SVGs. And so I can get a good idea of historic, where my air quality has been historically. So that big aberration there, that's me breathing on the sensor, which look at the VOCs. That's pretty good. That's pretty good for a Weedmaps employee especially. So I've already really talked about this first reason why you'd want to use nerves. So bullet point 1, concurrency. So you go out, you buy one of these, or you have one of these in your drawer. This is a Raspberry Pi 4. This has got a quad-core 1.5 gigahertz ARM processor on it. So this thing is, it's got quad-core magic, which is just awesome for Erlang and Elixir projects. You've got a to-do list, like what do I need this project to do? I need it to collect sensor data. I need it to store the sensor data to a cloud, and as well as locally. I need to, send it out to a display. So, why not do all those things at the same time? All right. Reason number 2, stability. And Justin talked a little bit about this yesterday, but I'm going to touch on some things he didn't really mention. And if you've used Elixir for a while or Erlang for a while, you're probably familiar with supervision trees, and you probably really like them. So in this case, like this is a sample supervision tree for my project. So I've got the app supervisor, and then we've got our cloud supervisor here, which is just in charge of maintaining the connection to Google Cloud and sending data up to that. I've got the init supervisor, which initializes some basic components like setting up the Wi-Fi, initializing the display, and then the output, which is output process, which is handling the LED matrix. And so, in your embedded system, if any one of these things crashes, it's no problem. The others are going to stay up. It's going to restart itself. It means you don't have to go plug it, unplug it and plug it back in, or climb a pole, or go to some remote place and restart the machine manually. So supervision trees are extremely helpful in all of our everyday programming, but embedded as well. And so I think of like supervision trees like this picture of Pinkie Pie. So you can see she's juggling these boneless chickens just like we're juggling processes in Erlang. And she's standing on a ball at the same time. And I think this is what I think of when I think of Erlang supervision trees. I realize now that I may have mental problems. It seemed like a really good idea when I put it on there. All right. Oh, hey. I know. So you guys are sadists, man. All right. He died, All right, so what if your program does this? All right, it crashes. You've got, power loss. You've got network inconsistencies. Am I going to turn this thing into a brick? No problem, Bob. Nerves can handle this. So there's some behind-the-scenes features of Nerves that can help. So Justin talked a little bit about this, but Nerves can alternate its boot partitions. So you've got 2 read-only partitions on your device where your application lives, or where the operating system lives and your firmware lives, and it's only using one at a time. So if you write to A and that thing crashes, you can still boot that thing back up to B and get it in a remedied state. I know, Elsie, it is too easy. All right, reason number 3, flexibility. All right. I don't know if this is fan art or if this is from the TV show or not. If it means something naughty, I apologize. It seemed banal. All right, so Nerves is happy to work with C, Python, Rust. A lot of embedded code is going to be packaged in these forms, or maybe you're more comfortable in these places. So you can think of Nerves as just being your operating system. So you get the benefits of supervision and Erlang stability, but you can run your C code on top of it. You can run your Python code on top of it. A lot of libraries, or a lot of device or hardware device makers will publish libraries for those sensors, like the BME 680. But oftentimes they're either published just in C or in C and in Python. So if you don't want to translate them over into Elixir or Erlang, you can use them as is on the Beam. All right, and last but not least, what I think is the most important reason why you should use Nerves for your next project is the community. The Nerves community is, well, I would say when I got started in the Elixir community, I was really, really impressed by how welcoming everybody's been. But joining the Nerves community is like even more so. So we're a small group of passionate people that are really interested in tinkering on hardware projects. Some of us do it full time. Some of us do it at nights and on the weekends. There's a few people that have formal training in electrical engineering, like Greg or Frank. And then there's people like Justin, who I think his formal education is in audio engineering. Yeah, audio engineering. And then, or Connor, the rumor is he quit school after 2nd grade and began teaching college. He's the, okay, he said it's close. Could be 1st grade, but he is the Leonardo da Vinci of our time. So the man can do just about anything. But yeah, I mean, you'll find most of us are just kind of tinkering our way through the NERVS projects. So if you have an idea and you don't know where to get started, or you got started and you got stuck, the community is great for helping out. So, and some ways to like kind of kickstart your project. You know, Doge here is talking about some really cool stuff you can do with devices like Bluetooth and ZWave. So I'll go through these quickly. So ZWave is, if you don't know, it's basically the networking protocol that's really commonly used for like smart home devices. And so we recently got a library to make this really easy to do in NERVS. So this Grizzly Library came out thanks to Matt Ludwig's and the team or the support of SmartRent. We've got a library now to communicate with ZWave. So if you know, smart door locks, etc. Sorry, battery might be dying. Let's try this one. All right. Talk too much. Okay, so yeah, if you've got any of those smart devices, there's a really good chance they communicate in ZWave, and by adding the Grizzly dependency to your NERVS project, makes it really, really easy to communicate with them. Bluetooth support. So if you've got an idea that requires Bluetooth, Daniel Spofford is Daniel, where's Daniel? All right, there he is. Thank you, Daniel, and the team at Very for producing the Herald library, which allows us to communicate via Bluetooth very easily on NERVS. WS2812 Neopixels. So if anybody has worked with LEDs before, stringing together 1,024, individual, okay, we've got one. Individual lights, which are not, it involves a lot of hardware, drivers, splitting pins out and stuff to address them. Neopixels makes it really, really easy to do RGB, like 24-bit color displays. And thank you to Greg and the Blinkchain library for making that easy. UI support, so you want to build a touchscreen, that's easy thanks to Scenic UI, thanks to Boyd for that. And for everything else, Elixir circuits. So again, thanks to the team at SmartRent, as well as a bunch of other contributors for supporting the circuits library. Circuits library is what makes it very easy to communicate through all the different common protocols. So SPI, I2C, which is what I used on this project, UART, and then standard GPIO. The Elixir circuits library translates all that into Elixir code, makes it very, 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 very easy to communicate. And lastly, so you know how to do it, you get stuck. We've got a remote meetup. We meet once a month, usually last Wednesday of the month, and it's online. So check it out at nervs.group. We'd love to have you join us, as well as the Slack channel. So we've got about 2,000 people in the Slack channel, new people joining every day. All right, so in conclusion, I just want to say, like, come join us. It's a lot easier than you think it is, and it's a lot of fun. If you know Elixir, you've already gotten through the hardest part of making a NERVS project. The rest is just common physics concepts, very well understood physics, and document. Maybe not well understood by you yet, but very unambiguous. And if you need help, you know, like I said, always reach out, and we're happy to help you out. And so finally, just say thanks again to the Gig City Elixir team for inviting me to speak here today. And I'd like to thank all of you as well. Without an audience, I'm just a guy talking to myself.